Hey everyone, Kevin here. Today we'll be talking about problem 10 of the 2002 AIME 1. Once again, if you need to open up the question in a new tab, feel free to do so. So this time we have a geometry question. We have a right triangle ABC. We have that 80, or I'm just jotting down the important facts. 80 is an angle bisector of A, shorthand for angle A. And EF are arbitrary points on sides AB, AC that satisfy length conditions. And this is essentially what the problem is. It is basically you have an angle bisector, you drew a random line somewhere down the middle, and you're trying to find the area of some quadrilateral. So once I see this, I immediately think, well, I can coordinate match this. So, and by that I mean I can set, or just set D equals to the region, B equals 0, 0. I can find out the coordinates of D pretty easily from the angle bisector formulas. We'll get to that in a second. And from there I can just find E, F, G, and then I can just use the shoelace theorem for the area. Or I can do some other way that also uses coordinates. So coordinate bashing is a pretty straightforward way to solve this question, but it might not be the fastest. And maybe we want a synthetic solution instead. So let's first try to see if we can find a synthetic solution to this. Okay. So first we notice that it is a right triangle. So ABC is a right triangle, and we're given two of the side lengths. So we can calculate the length of the third one. So BC is equal to the square root of 37 squared minus 12 squared, and some easy difference of squares gives this to be 49 times 25, which is 35. So that is BC. And now, because the AD is an angle bisector, so we have these ratios, which are pretty important. And you should definitely memorize them if you haven't already. So AD is an angle bisector, which means AB over, not AD, BD equals AC over CD. And this is nice because we know BD plus CD equals 35. So essentially we have two equations with two variables, because we know AB and AC are 12 and 37 already. Okay, so let's first convert that ratio. We have 12 over BD equals to 35 over CD. So to solve this really quickly, we can just let x be some variable such that 12x is equal to BD and 35x is equal to CD. And this immediately satisfies our second relation, the ratio. And then we can just add, so x is equal to 35 over 12 plus, oh wait, is that 37? That is 37. Okay, so it is equal to 35 over 12 plus 37, which is 49, so this is equal to 5 over 7. And I get that BD is equal to 60 over 7, CD is equal to I got confused again. This is 37. 37 times 5, which is 185 over 7. Okay, so now that we found BD and CD, we can actually just begin coordinate matching, but we'll try to find a synthetic solution instead. So looking at how you can find the area of CDF-GF. Basically, for these type of geometry questions, we want to kind of just, because the values can be quite messy to work with, a lot of the times we just want to proceed to solve a question by not calculating stuff out, and instead just using whether the fact that you can calculate it. For example, you can solve a quadratic equation with a bunch of nasty variables in it, like a bunch of nasty coefficients, and doing that discriminant might be tedious, but you can do it, which is something that you can use to solve like some question. So in this case, we want to find the area of GFCD, and looking at it, there are a few different ways we can calculate this area, but one of the most straightforward seems to be just the area of, or the difference of areas in two triangles, ADC and AGF. So ADC minus AGF, okay? And how can we find these? Well, looking at it, what is ADC, or the area of ADC? How can we represent this area? Well, there are a number of ways to calculate the area of a triangle, but in this case, one method kind of is very striking here. That is the 1/2 AB sine C. And why is this? Because we know a lot of lengths, or we know AC and CD. So we know two lengths in this triangle, but we also know all the angles, okay? Some of them might be a bit tricky, because we already know C, or at least sine of C. We know sine of C is BC over AC, but we also know the angle of D, or DAC, because it's half the angle of A, which might be, once again, a very somewhat tedious to calculate, but it is possible to calculate it. So we can conclude that area of ADC is known. So now all remains is to find the value of the area of AGF. So AGF, how can we do this? Well, one thing we know that we can also apply the same thing again that we did for ADC to AEF. As in, we know AE, we know AF, and we know the sine of angle A. So area of AEF is known. And AGF is a part of that. So we can try to find the area of AEG, but that we run into a pretty big problem is that it doesn't seem to work as well because we don't know the area, or we don't know the lengths. EG, AG, FG, we don't know any of these. We don't even know EF, for example. Actually, we can calculate EF. Oh, that is interesting. So we can calculate EF. So EF is known through log cosines. on AEF, because we know cosine of A, we know AE and AF, so we know EF. And since we can calculate that, and since AG is an angle bisector of AEF, we can calculate using the same process as before, EG and FG, which basically solves the question. Because then we get AGF. We get AGF pretty easily because of the other formula. The other formula that you should memorize for angle bisectors is that this follows from Stewart's theorem. AG squared is equal to AE times AF minus EG times GF. So this means that AG is known, and thus Heron's on AGF times the area. But of course, this is very nasty. It gives you a lot of bad values. You don't really want to find these values. There's going to be a lot of square roots and stuff. So instead, you might want to consider a slightly different approach to finding the area of AGF. Though this method, of course, works. As long as you do all the calculations correctly, you're able to solve the question using this. And that is the kind of the beauty of math. You can have multiple solutions to the same problem. I guess depending on your level of insight, one solution might come easier to you than maybe to others. So another way we can approach this question is that we can look at the ratios in this triangle, specifically the ratios of the area of AGF to the area of AEF, which we know. So note that the triangles AEG and AEF have the same height. And this means that their areas are, so basically, we have that the ratio between their AEG, AEF is equal to, or rather AFG, because we want that, is equal to FG over EF. But we also have, by a law of sines, because sine of AGE is equal to sine of AGF, and because AG is an angle bisector, we have the unique property of that AE, which corresponds to the angle of AGE, over AF, which corresponds to the sine of the same angle, so the sines are equal, is equal to EG over EF, or GF. Because of angle properties. And it might take you a bit to see this, so feel free to pause and see exactly why you have this ratio in the law of sines. But because of this, so using these two formulas or equations, you get that AFG, or rather the area of AFG, is equal to AE over AF, AE oh, okay, Yeah, I did a little miscalculation here. This is AE over AF. I mean, this is EG over GF, not FG over EF. So this instead is going to be AF over AE plus AF, I believe, times the area of AEF. And this, because we know all these values, this is 10 over 13 times AEF. And AEF is known, it is equal to, and this is when we start doing the calculations, 1/2 times 3 times 10 times sine of A, which is 35 over 37. And this is equal to, doing some quick maths here. We have 150 times 37, 35 over 13 times 37, right? Something like that. I believe that is correct. Yeah, okay. And solving for, what was it? ADC. ADC is 1/2 times CD, we found, was 185 over 7 times 37 times sine of C, which is 12 over 37. So we get 180, just say it's 185 times 6 over 7. Okay. And we can just do some calculations here. I really don't want to solve this, but I suppose it must be done. This is why I like modern AIME problems much better. The area of GFCD, or rather, the problem DCFG, is equal to 185 times 6. Let's simplify that a bit. 185 is 35 times 7, no, it's 37 times 5, so it's 30 times 37 over 7 minus 30 times, what's 35 times 5, 175 over 13 times 37, right? Okay, is equal to 30 times 37 squared times 13, so denominator will be 7 times 13 times 37, 175 times 7, right? Not looking pretty at all, is it? That is actually 7 squared times 37, right? Or, it is, no, 7 squared times 35. I thought I could pull some, difference of squares magic here. But no. Hang on, let me just get my calculator real quick, because I really don't want to do this calculation. 85 times 6 over 7. So I'm getting an answer of 147.6. And what did we want? Integer closest to the area, so that will be 148. And so we're done.